Okay, solving trigonometric equations, another area that gets students extremely confused. So let's just debunk all that confusion and make it easy for you. Just systematic, steady as she goes, wins the race. Now we've got to solve sec of 2x equals 2, where x goes from 0 to 2 pi. This is the Wolfman approach. Firstly, find the working domain. Okay, the working domain. So if x goes from 0 to 2 pi, I need to know what's in here, what's in that bracket's going to go for, because that's what I first have to solve for, right? That's what I first have to find out. So, okay, 2x will go from 0 to 4 pi. Now, that's really what I'm going to be working with to capture all my correct solutions before I finally solve for x. So that's the working domain. Secondly, we convert this so that it's cos, because cos is what I'm familiar with. So, therefore, cos of 2x equals a half, doesn't it? Yes, where 2x goes from 0 to 4 pi. So that's basically what I'm going to solve for. Let's do that. We solve the equation using the working domain to capture all the solutions, yes. Now, in quadrant 1, the angle, this says the angle whose cos is a half in quadrant 1 is pi on 3, isn't it? It is. Okay, so now we'll have a look at what quadrants we want. We want this one, and we want this one where cos is also positive. So we've just got to whiz around that cast diagram, capture everything which qualifies in quadrant 1 and quadrant 4 between 0 and 4 pi, and that's what we do. Using the cast diagram, so 2x would be pi on 3 or 5 pi on 3. Now what you do now is you just keep adding 2 pi to here and to here, leapfrogging across here until you get out of range, and out of range means you can only go as far as 4 pi, our working domain. So that one, and what's that come to? Yeah, 11 pi on 3 looks like the last one because that's very nearly 4 pi. Yeah, because 4 pi being 12 pi on 3. So now, when you get to that stage, ladies and gentlemen, then you just basically solve the thing for x. And there it is, there's the answer, okay? Yeah, and using technology, here it comes over the screen. So what you just type in here is solve sec 2x equals 2 for x with x going between 0 and 2 pi, and you get the thing in a snap. Yeah, it's very good, isn't it? Now another one, find the general solution to cot 2x equals minus 1. Now this one's a general solution, so there's no working domain for this. We have to find a way of expressing the infinite number of solutions which apply to this, and we don't do working domain because there isn't any such thing. We're not restricting the domain. So, the same procedure as before. No working domain, general solution required. Secondly, express the equation in terms of tan. So tan 2x would also be minus 1 because 1 over minus 1 is minus 1. And now we work out the solution to this in terms of 2x, and then we basically solve it finally for x. Okay, thirdly solve for x. Yes, now here's our cast diagram. That's where tan is positive. No, it's not. It's where tan is negative. What am I saying? Yeah, these are the quadrants we require, where tan is negative. Okay? So, what are we saying? We're saying in quadrant 1, the angle whose tan is 1, that's what that's saying, the angle whose tan is 1 is pi on 4. So therefore 2x equals minus pi on 4. Now I've gone down here, I've called this angle, a negative angle here, I've called it minus pi on 4 plus multiples of pi, because that also encompasses this one here, right? That's the way you can express tan, because tan repeats every pi. So you just say, okay, pick an angle and then just keep adding pi or multiples of pi. When you have to put this in here where k is any integer. You must put that bit in there, otherwise you're wrong. Then you solve it for x, and you get, oh, that's the alternative. Yeah, you could have said 3 pi on 4. That's fine. Plus any multiple of pi, that's also fine. There's many ways that you can actually say this, which all amount to the same thing. That's what I get there. I've divided by 2. So x is basically minus pi on 8 plus k pi on 2, where k is any element of z, z being all the integers. That means positive natural numbers, negative whole numbers, and 0. Now, alternatively, yes, that's right. That's good. Now, yes, I'm saying there any variant using quadrant 2 or quadrant 4 angles may also be correct. So don't get all hung up about the fact that the answer in the back of the book might look different. it's probably the same thing, and the only way to really find out is to test it. Technology, yes, that's the same thing. Now, this thing here is just a parameter. That means x is, you could use that as your k thing like I was using, okay? So 4k over 8 is really just k over 2, if that's just the way the calculator did it. So I would be saying that would be equivalent to minus pi on 8 plus k pi on 2, okay? That's right, from the previous screen. Okay, good. Now another one. Sec of this beastly looking thing is equal to that. Look, it's the same procedure, exactly the same procedure. This time we do have a working domain, don't we? So let's work that out first. This is where x is defined, so we better work out where the thing in the bracket here is defined, capture all our solutions, and then finally solve it for x. Find the working domain, so if x goes from 0 to 2 pi, work it up bit by bit. Therefore 2x would be from 0 to 4 pi, therefore 2x minus pi on 3 would be, if you work it out, from minus pi on 3 to 11 pi on 3, and that's our working domain. Right? That's how you capture all your solutions without doing the scattergun approach and kind of like, you know, doing too many and then having to cross them off. And I don't like that approach, but a lot of people do. Whatever you like, as long as it works. Secondly, express the equation in terms of cos, because cos is what we're familiar with, so therefore cos of 2x minus pi on 3 would be the reciprocal of that. Yes, it would, wouldn't it? And another way of writing that, which we are familiar with, would be minus root 3 on 2, because you can divide root 3 into 3 root 3 times. Okay? Now we're getting somewhere now. We better have a look and see what in quadrant 1 that would be. Thirdly, we do solve the whole thing for the working domain to capture all solutions. Yes, so in quadrant 1, apparently we're dealing with, here we are, the angle who has a cos, the angle whose cos is root 3 on 2 is pi on 6, isn't it? Yeah, that's right. So we want negatives. So basically we want this quadrant here, and we want that quadrant there, quadrant 2 and quadrant 3, because we want the thing to be negative root 3 on 2, okay? So, using the cast diagram, we've got to whiz around here, backwards to minus pi on 3, and then separately forwards as far as 11 pi on 3, capturing all our solutions. Okay, so I've worked it out. I've said, alright, 2x minus pi on 3 is going to be 5 pi on 6, that's the first one from here, 7 pi on 6, and then adding 2 pi there to the first, to the 5 on 6, 5 pi on 6, to the 7 pi on 6, and then again, I think that one might be out of range. I think it might be out of range. Just let's have a look here. Yes, because that's, how many pi on 6 is that? It's 29 pi on 6, which is 14.5 over 3. And it's out of range because we're only allowed to go to 11 pi on 3. See, and 14.5 is more than 11. Okay, are you getting that now? And of course there's no solutions going backwards to minus pi on 3, because that would only get us backwards from here, going around that away. That would only get us to somewhere in quadrant 4, which doesn't capture any solution, so I haven't bothered to put that on the working here, but that's true. So really only the forwards ones, the forward sweeping produces solutions. Now we solve this now. Okay, we just make it a bit simpler to look at. So therefore 2x minus what oh yes, I've put it all over 6, right, to make it easier to do the next step. Pi on 3 is 2 pi on 6, and I've got all these things in terms of 6's, haven't I? Yeah, so now, so the thing in the bracket over here, right, that thing there is equal to all these angles which I've just produced within my working domain. Now I've just got to solve it for x. Right, so therefore adding 2 pi on 6 or pi on 3 to both sides, you get that. Dividing by 2, you get that. And lastly, you would simplify by working out if there's any cancelling down that can be done, which there would be. You can see there, that'll be 3 on 4. That won't do anything, that won't do anything. This one will, because 3 will go into both of them. So therefore you get that. Alright. That's it. I know it's tedious, but look, you know, it's pretty easy to do. With CAS, it's so easy. Look at it. It's just, it's embarrassing how easy it is compared to using our heads. But it's good, you know, it's great. Okay, so what's this? Solve for x goes from 0 to 2 pi. We've got some equations to solve here, where we've got trig stuff on either side of the equation. So, alright, so we've got sine 2x equals sine 4x, and secondly we've got cos of x on 2 equals sine of x. So some double angle formulas to use here, and we just learnt them in the last two lessons ago. So let's go for number A today, hooray. And we'll say that sine 2x equals sine 4x. Now you can re-express sine 4x as 2 sine 2x cos 2x. Now don't go cancelling off the sine 2x. Oh, please don't cancel that off one side from the other. You will lose solutions if you do that. You will lose a solution. You are allowed to cancel the numerator and the denominator terms involving x. Numerator and denominator you can, but not on both sides of the equation. Otherwise you'll end up coming unstuck. So you do that instead. You leave that sine 2x alone and you factorise it out like that. Now, by the null factor law, you can say therefore sine 2x equals 0 or cos 2x equals a half. Now you've got to solve each separately, right? You've got to solve each separately, and I suppose I should have worked out my working domain, shouldn't I? Because the x goes from 0 to 2 pi, so 2x is going to go from 0 to 4 pi, isn't it? So, yeah, there it is there. I did remember. So, you see, I must have written all this because my head knows what to do, and in the way that I do it. So, therefore, if x goes from 0 to 2 pi, 2x goes from 0 to 4 pi, my working domain. So, first of all, we'll work out, we've then got to solve for x using our cast diagram, okay? So first cab off the rank, the first one from this solving using the null factor law, sine 2x equals 0, where 2x is allowed to go from 0 to 4 pi. That's what it is. Just draw a little graph of sine, you have a look. Okay, it's 0 every pi it goes through 0. So therefore, yeah, see? Told you. Therefore, x will be going just halve everything. There, you got that one done now. Now, what about the cos one from this bit over here? Cos 2x is equal to a half. Okay, so these two quadrants we want. Now, what angle has a cos of a half? It's pi on 3. Therefore, let's whiz around from 0 to 4 pi and see what we can dredge up. Yes, pi on 3, 5 pi on 3, then add 2 pi to the first one, then add 2 pi to the second one. That's enough. Otherwise, we'll be out of range. That's what you get. You can see that that's almost out of range because that's 4 pi would be 12 pi on 3, so you'd cross over out into the out of range realm. See, that's the beauty of the working domain. You know exactly what you're doing. So therefore, x would be that. Now we better express the whole thing as a combined solution, putting them in order and all nice and neat. So I've snuck the other ones in here. What were they? Those ones, right? I've combined those in there, put the whole thing in proper order. I got with that amazing array of lineups there of the solutions. Okay, with CAS, it's embarrassingly easy. So we're just solving for that thing there equals that thing there with that there, and it just spits them out beautifully and dutifully. Now, what have I got here? This is another one. This is another double angle-y thing from 0 to 2 pi. Yes, I just went double angle, right? It's obvious what to do. Go double angle, blah, blah, blah. Don't cancel out the cos x on 2. You'll come unstuck. Don't do that. Working domain, we've got x goes from 0 to 2 pi, therefore a half x this time. Half x goes from 0 to pi. That's our working domain, right? Now, you solve the thing, and then you solve the thing for x using the cast diagram, or x on 2 and then x, it doesn't matter, you know what I'm trying to say. Therefore you do that, you factorise out the cos x on 2, you get that, null factor law says that. Alright, now we've got to solve each of those separately. If cos of x on 2 equals 0, just think about the cos graph. Yes, x on 2 would be pi on 2 or 3 pi on 2. The first one in a cos graph is pi on 2, then every pi after that. Okay, so that's good. So therefore we better, and what are we saying the domain for this working domain is? Yeah, 0 to pi. That's 0 to pi. X on 2 goes from 0 to pi. Well, wait a minute, I'm having a think. Well, that second one's out of range. Oh, I tricked myself. I did know it was out of range, okay? But you immediately know you're out of range when you've got a working domain. So, therefore, x on 2 is only pi on 2, therefore x is pi. Only one solution out of that. Now we better do the other one, where sine x on 2 equals a half, using the cast diagram, and x on 2 is only allowed to go from 0 to pi. Well, oh yeah, you'll get two solutions out of that, yes, because these two quadrants are both positive, and we're allowed to go up as far as pi. So therefore, the angle that has a sine of a half is pi on 6, therefore you're going to have x on 2 will be pi on 6 or 5 pi on 6, therefore x will be pi on 3 or 5 pi on 3 for you and me, and there's, now we'll combine those two solutions there and put them all in nice or neat order, and we'll get that. Yes, oh my hat, we got that. So, goodness, we're cooking along nicely. With Kaz, again, embarrassingly easy. See? Solve cos of x over 2 equals sine of x for x. With x going from 0 to 2 pi, you get that. Yeah, it's very easy, isn't it? Right, now this is the last bit of our presentation. This is pretty interesting stuff. Now this requires that you use your head a little bit. First of all, you look at this and you think, oh my hat, how am I supposed to work this out? Maximum and minimum. Well, what you do, guys and gals, is you put your problem-solving hat on and you look at it and just wait for the answer to come and rest on your brain, okay? That's what's going to happen, because I'll show you how easy it is. I'll show you how easy it is. And it really does come and rest on your brain when you do a lot of practice, because you just don't get tricked anymore. So I'm going to complete the square. Look. So I've completed the square, as you're aware, and I've got that. Now, what am I supposed to do with that? Well, you know what I'm supposed to do with that. Look, you now use the maximum and minimum values of sine of 2x and see what that does to this, right? Now, when I say the maximum and minimum values, okay, the maximum value of sine x is 1. Yes, isn't it? And you've just got to make, that'll get you the maximum value of this squared term, I think, won't it? Now, what would get you the minimum value of this squared term? Think about that. Well, if we went minus 1 for sine 2x, which is the minimum value, that would make that whole term in the bracket 0, wouldn't it? Yeah, and if you made it 0, that'd be no good, because that'd make that 1. So I'd say the maximum occurs when sine 2x is 1, which gets you 2 in the bracket, which gets you 4, which gets a total of 6. Are you right? And if we went minus 1 for the minimum, that would get you 0 in there, which would get you 2. So I'd say the minimum's 2 and the maximum's 6. I hope that's right, but it's been a hot day and my brain's cooked. Let's see now. Yes, that looks pretty logical, doesn't it? Yes, very good, 2 to 6. Ha. Isn't that a good feeling? Isn't that a good feeling? So you can do that. Come on, standing on your head. Just put your problem-solving hat on and you can do it. Now, part B for you and me is pretty easy, because it's just 1 over that, right? So whatever was the minimum in part A is going to become the maximum in part B, and whatever was the maximum in part A is going to become the minimum in part B. So I would say the minimum is 1/6, and the maximum is going to be a half of the reciprocal, wouldn't it be? Am I getting ahead of myself? Oh no! Look, we're cooking along, cooking with gas, as we say in Australia. So this is really excellent. So are you happy with that? You just play it cool, be systematic. You will conquer. I'm telling you, you will conquer these things, these trigonometric equations. And you're a star, and huzzah, and you'll go far. And it's time for a nice cup of tea, and time for me to get out of here and spend the rest of my evening relaxing, and I will see you next time. Okay, bye-bye.